Good morning, folks. This is tutorial number 40, and it is in the dynamic scenario playlist for 3D Experiences platform. Uh, in tutorial 39, I showed you a very simple mass spring damper system where the steady state response of the vibration was obtained. In other words, if you displace the mass uh, by some amount and release it, that will go back and forth forever unless there's a damper present. And what we like to know is model that steady state response. And I mentioned that there will be a follow-up tutorial, which is this tutorial 40, which is a bit more complicated, not hard. The only difference, the main difference is that, for example, I don't have a spring as I did in tutorial 39, which created the restoring force for vibration. Here, I don't have a spring, but we still want to do the problem. Actually, this is taken out of a second year dynamics textbook by Merriam and Craig. And the exact statement of the problem is over here. It says, if this shaft turns at constant angular velocity omega, what would this in the steady state, what would this angle of tilt be? And uh, basically writing the equation of motion in 3 dimensions, of course, and setting all the accelerations equal to 0, angular acceleration in this case, and you're going to come up with this answer. The angle is actually given by that expression. So what I'm going to do, I will model this problem for you, assuming that omega is at 120 RPM. The B is 200 millimeter, this length B is 200 millimeter, and this length C is 100 millimeter. These are the dimensions, don't matter, and it's the gravity is 9.81 meter per second square. The mass of these things, although have to be specified because we're using the dynamics uh, module, but they're not going to come into the calculation. You can see that there is no M here. There is no lateral size dimensions here. Okay. Now, if I use these values, that formula will give me approximately 18.1 degree angle of tilt. So, what I'm going to do is, now notice that in order to get the steady state, you need to have a damper, and that damper must avoid the oscillation up and down of that rod, which means it has to be a torsional damper, essentially. And we cannot do that with axial spring as I did in tutorial 39. We have to create a bushing. Okay, we will do that. But initially, I will not create that bushing. I will pretend that this thing is turning and when the gravity deflects and show you how the motion takes place, not which is not going to be steady state response. We will get to there. The way I'm going to do that is basically create three parts. There is going to be the bar, there's going to be the shaft, and there's going to be a base like that. And when you put it together, obviously you're going to get that. The purpose of these access systems is later on when I want to create the bushing, I need these two, okay? And here is what happens if I create the bushing. You can see that as the bar as the shaft turns, this is the trace of that point and eventually stabilizes and it goes around that circle, which is really the steady state motion of the bar. Okay, I will show you what happens if I don't have the damper, what goes on. So, all right, let's go ahead and do this. I'm going to insert my first part. So I'm going to do the rod first. So right click or the bar first. Okay. Insert 3D part, and this is going to be my bar. So I'm going to right click, change the name of it. It's going to be the bar, which is just a rectangle padded, and Here's the bar. And while I'm at it, I'm going to change the color of it to green. Okay, let's go make it. So we go to the part design. This may take an extra 4 or 5 minutes, but at least I'll show you all the steps to create the model instead of saying that here's what I did, put it together. So, all right. So, for example, on that vertical plane, I will sketch. I'll sketch a rectangle. Let's give it some dimensions. This is going to be total of 300 millimeter. And just for the sake of concreteness, I'm going to make this thing 10. That doesn't come into the picture, but anyway, makes it easier for me to create the model. Now, uh, exit. There's my bar, and I'm going to pad it just to make my job easier symmetrically by let's see how 2 looks like. Yeah, that looks good. Okay. Then I want to make that pin on the side. You can see that there's a pin here. The pin the way I'm modeling it is I'm attaching the pin to basically the bar. So I'm still in the bar. So on that same vertical place, I will sketch. Let me go and draw a circle here and make sure that, well, I'm going to make the radius of it maybe 2. These are irrelevant, but for the sake of concreteness, I'm going to do that. And then I'm going to place it exactly halfway between the top and the bottom, which means you can dimension it if you want from the center of this to this to be 5. Okay. Also, yeah, also I want this center to be 200 millimeter away from that edge. That is this 200. All right, exit. And then I'm going to pad this thing symmetrically. If I do this thing, remember this thickness is I think we made it 4, so I make it now. Let's make it 8. See how it looks like. Maybe yeah, 8, 6. Let's see how it looks like. Well, 6 millimeter, not 6,000. There. That's that's a lot better. There we are. Okay, so this is my rod. Now, then I'm gonna go and insert the how about doing the shaft? So insert 3D part. I'm gonna call this thing the shaft. Please, if you feel free, please feel free to move forward if you find these unnecessary that you can do it. That's okay, but I'd rather show all the steps. Shaft, okay, and let me change the color of it. Forgot to do that. I'll make it orange. Okay, let's go make it. Okay, so the way I'm going to do that on that vertical plane, I'm going to create these things in place so that it's easier for me to basically do the problem. So here is how the shaft is going to look like, at least part of it. I'm going to go like this. We'll clean it up. Okay. And I'm going to make this guy control that circle. We'll make them concentric. Hang in there. Let me try it again. We zoom in. this circle, control that circle. I'm going to make them concentric. Now it's nice. All right, and oh yeah, and then I'm going to project that circle on it to make a hole there later on. So I'll make a projection. That circle. It's okay. And exit. There we are. And then we make a pad in both directions. Let's make this thing 12 and see what happens. Maybe 6. Let's see. Yeah, that looks good. Now, on that face, I will sketch a rectangle. Maybe something like that. Actually, let me do the following. I'll make a rectangle like this. Running out of all kind of problems here. Okay, let's try it. There. That's what I want. Okay, let's make it nice and symmetric. You know, this control that, control the middle axis. You're going to make it symmetry, exit, and make a pocket all the way through. There we are. And finally, on the top, I'll sketch a circle. Okay, let's make it symmetric between top and the bottom. This control that point, equidistant. Very good. Exit and pad it up. That's too much. Move this thing down here a little bit more. Yeah, that's good. So that takes care of my shaft. We go all the way to the top. We're going to insert the what do I call the base? I think we called it the base. Yeah, base. Right click, insert 3D part. Call it the base. Base and base. It's just a cylinder. That's all. I'll leave the color gray as it is. Double click on that plane. I will sketch a circle concentric with that. I think this is concentric. Exit and pad. The other direction. Wrong way. Reverse, and I'll make it maybe 8 millimeters. It really doesn't matter. There we are. This is going to be my base. Okay. Now we go all the way to the top, all the way to the top, and save everything. Okay. So let's go ahead and apply our constraints or engineering connections. First thing we're going to do is to fix the base. So we go to engineering connection, fix, and it's going to be the base that's going to be fixed. Okay. Then I'm going to create a revolute between the base and that shaft. So a revolute joint. And I will use this template. So for the axis, this axis and that axis, for the plane, maybe this plane and that plane. And because I want to specify the speed later on, I need to define the the planes which define the angle. So, for example, between the shaft and the base, I'm going to use these vertical planes. Okay, so that'll be, for example, I don't know, maybe YZ. Okay, YZ of this and YZ of that, or XZ and XZ, doesn't matter. There we are. So we have created a revolute joint, and then I need another revolute between this hole or the bar and the shaft. So another revolute, same template. Okay, so I'm going to use the axis of this shaft and the axis of this hole and the vertical plane of that'll be XZ plane, yeah, XZ plane of the bar and the XZ plane of the shaft. And I don't need to control it. Just delete that. Then we say OK. Gravity is going to bring this thing down. We don't have to control that. Okay, very good. Now, let me see for a second. We are done here. We're going to go, let me save. We're going to go to mechanical systems design. So we'll create our joints. All right, remember, this is where we have the spring. I don't have a spring in my problem, and the bushing and things are, but we're going to come back and do that thing later on. Right now, let's go and create our mechanism. Here's the mechanism representation. Say OK, and then see what's in it. Obviously, there is one fixed part and two revolute joints. Very good. OK, let's move on. Now we define the mass properties. So weight definition, actually mass definition. Everything is red, nothing has been defined. So let's start with the bar, and it says if you want to define the mass property, click on this link. I'm going to assume it's made out of steel, okay? And basically this is the mass of it. The mass does not come into the picture, so just leave it the way it is, okay? Say okay. Yep. Then I'm going to go to the shaft. Again, click on that link, make it out of steel. Done. And now the base again is stationary, but we have to specify the mass property on it because it's part of dynamics analysis. So everything is blue, that means the mass properties have been defined. And that's pretty much it, nothing else to do here. So now we're going to go to mechanical systems experience. This is where the dynamics module lies. All right, now gravity acts. See, here's the gravity icon. Click on the gravity, minus 9.81 in the Z direction, negative Z direction. Very good. Let's also go and create our dynamic scenario. Just click on it. Gravity excitation, you include it. And we're going to do it over, let's say, hypothetically 10 seconds. Remember, there is no damping here. We just go run it. Assuming that I didn't forget anything, right click. Wait a minute. Oh, the motor speed and things like that. Whoa, whoa, this is gravity, of course. This is not turning. You can see that. This is not turning. The shaft is not turning. That's why it does this. But anyway, we want the shaft to turn. So it's complete. I forgot. So let's go back to scenario. Okay, good. Here is the let's see now. Velocity excitation. Velocity. Okay. Velocity motor excitation right there. See this? Right there. We're going to put it on that revolute. this command that I created, and this is going to be 120 turn underscore min, which is yeah, basically it's 4 pi. That's what it is. And then we say okay. Now we're going to have this thing turn. So let's see if it's included. The excitation must have been included right there. All right, let's go ahead and run it. Okay. So it looks like the bar actually tilted, but I'm going to show you the path that that bar will take, the tip of the bar will take. And I can assure you it will not look like this. Okay, so let's go ahead and find out. How do we do this? We can go and get the geometric trace right there. See that geometric trace? Which point? For example, this point. This is the path that it takes. In fact, you can take this and put it where it was. Let me take this. Let me take this geometrical. Let me see. Copy this. Can I go put it back there? Let me see if I can put it here. Paste there, and you can animate it if you want. You can go and animate it, and you see what happens. And let me put this thing sideways so you can see. It starts on the top, then it goes back and it moves around. So let me go ahead and here and run it so that you can see. Well, actually, this is in the results. We can actually do the play the video right there. Look what happens. So now, whether this is a chaotic motion or some kind of periodic motion, I don't know. But that's really not the point of this exercise. We notice that without damper, uh, this will not settle down. So let me get rid of that. I'm going to delete that thing that I inserted, this thing that I inserted. Let's see, can I hide it? Oh, actually, let me go ahead and delete this. Actually, go there. Can I delete this? Yes, now I can delete it. Delete. It's gone. Okay. So the question becomes, how do we put a damper there? And that's where we need to do two things. I need to create two coordinate systems, two axis systems. Let me show you what happened. I need to create two axis systems, and let's do that. So we go here. Let me hide, first of all, let me hide the shaft so that I can see it better. We go to the bar, we are going to the bar, this is part design in the bar, and there's an axis system here, you see this? Axis system, you click on it, it puts it by default there. I want to put it right at that pin. So for the origin, I'm going to say, okay, create a point. Where's the point? For example, the center of there. Okay. And then we say, and let me uncheck this. Doesn't matter really. So it put a coordinate system here. It just happens that this is Y and this is Z. You can change these things so that it's, if you want, so that it looks like that. But it really doesn't matter. Doesn't matter. Okay, good. Now we're going to do the following. Now we're going to go hide, bring the other one into the show mode. So that was the shaft. Let me bring this thing into the show mode and hide that fellow. And I create an access system. I have to go there. I have to go to this shaft, first of all, import design. axis system, and I'm going to create one for the center. I can use the same place, but I'd rather do a different one. So I'm going to create a point and center of maybe center of gravity. That's fine. Of this, it created it right there. The location of it doesn't matter. Create. Notice that the y's are lined up. Okay, because later on when I uh, define the damping coefficient, it's going to be about some axis. It's going to be about the y-axis, for example, this axis. And then, yeah, that's fine. Good. So let's bring everything into the mode, show mode. So what's missing here? The the bar. The bar. Wow, I can go there. Okay, the bar is hiding. Bring it in the front. Okay, very good. So we want to create a bushing. So what we're going to do is we go to our uh, mechanism, mechanism, mechanical systems design, okay? And we are there, and there is a bushing. Click on the bushing. Notice that what happens is select to support. The only thing that you can support are those access systems. The order doesn't matter, by the way. And we want to define damping. Click on the damping tab. It's about the y-axis, right? About the y-axis, and we put down any number. So, for example, let me just randomly put 10, and then say OK. So now we have a damper, torsional damper there. So let's go ahead and run it. We go to our scenario, right-click. Oh, I want to show you something very strange. Uh, you'll see that the result is not going to change from what I showed you. And this happened in tutorial 39, and I want to remind you why. Let me go ahead and run it. Actually, we have to be there to begin with. Let's go there first so that we are actually in mechanical systems experience. Right click, run it. This is exactly the same thing that we have. It's not stabilizing. And this happened to me in tutorial 39 because after I created the bushing, I forgot to include it in my mechanism. Okay, we have to do that. In fact, you can see what I mean by that. Let's wait for this to stop. Okay, good. Look, in my mechanism, I don't have that bushing because you double click on this, you click on the mechanism manager, that spring, which is really my bushing, was not included. Now I do, and now I'm going to run. I may have to go and change the, see that? Give it a second. That damping probably was uh, too high. So let's check some few things. Okay. So first of all, let's look at the trace, geometric trace. For example, that point. There we are. Okay. And that damping probably was too high. So what I'm going to do, I'm going to go back here, reduce the damping value to let's make it 1. Where is that joint? That fellow? The bushing is right there. I'm going to change that thing, damping about Y. I'll make it 1 and run. Okay, let's look at the trace now. Trace of that point. There. So it started here, and then it went down and it settled. You can see that. Let's go ahead and let's do the same thing. So right click, copy. We go to our mechanism of simulation. Where was it? Here, there, and put it in. Paste. Did I copy that? I'm not sure if I did it. Just a sec. It was this, yeah. Copy. Okay. Double click on that. Now we paste. There we are. And let's animate this thing. Let's go to the results. And there. Okay, so let's see now. It's going down. You can see that. You can see that. As a matter of fact, let me do the following. Let me go to my scenario, and instead of 10, I will do maybe 20 seconds. It's going to take a little bit longer, but that's okay. We can see what happens. Do it. It looks like that bottom curve is actually the stabilized orbit. Okay, now, how do we know the numbers are right? Okay, this looks good. So let's go and plot a few things. Remember, without the damping, this will go in a more or less chaotic way all over the place, up and down and things like that. So let's check something here. Everything takes longer because I did it for 20 seconds. Now let's go plot something, and that is the downward displacement. I need the downward displacement, which I neglected to do. So let me go ahead and go back there. Forgot to put a probe there because I want the downward displacement. And I'm going to go make a probe, position speed probe of a point. For example, I don't know, this one of these corner points. It doesn't matter. I'll take this one because I can select that. Create a probe. Make sure it is included in my scenario. It is included. And I'm not going to go 20 seconds. I'll go 10. And we're going to run it again, unfortunately, because I had to do the probe. I forgot to do it. Okay, just give it 10 seconds. It's going to go stabilize down there. And I'm going to look at the vertical displacement. The ratio of the vertical displacement to 200 millimeter will actually be the sine of that angle. And if you take the inverse sine, I should be getting the analytical, or the thing that I can compare with the analytical result. Just a minute. Okay, so plot. With the Pro, I have a whole whack of other stuff that I can plot. Among them is the vertical displacement. There. Deselect everything and look at the downward displacement Z vertex and plot. Note that it's stabilizing. And if you want number, more or less, I mean, if you go 20, this is going to be more flatter. If you go here, this is the vertical displacement, 37. But one thing I want to do is actually, since you may not be convinced that this is actually steady state, what I'm going to do is I eat my words and I'll go make this thing 20. Let's go run it. Yes, it takes another couple of minutes, but then I have a better confidence in that I'll reach the steady state value. And I need my calculator because I have to do the sine inverse of something. So while this is running, let me get my calculator ready to go. So a sine of whatever I get divided by 200. 200 is that length B. By the way, that thing that I got for you, the thing that appears in the plot is not the displacement, it's the coordinate. So you have to be a little bit careful about that initial height of 10. Okay, so what I mean by that is this: be careful here. When you try to match the analytical solution, if you take that vertical displacement, it was already 10 millimeter kind of above, or 10 millimeter above the above that horizontal line. See, it's more, looks like it's more steady state situation now. Now, what I was going to say is that this number is, you have to subtract 10 from it. So that'll be, let's hypothetically say 48.6, 48.6 divided by 200. So a sine inverse of that, and in degrees, let's see what it is, you get about 14 degrees. But keep in mind that this has not reached the steady state yet. You probably have to go past this 20 seconds. Okay, but anyway, you get the picture. So right, good luck.